So yeah, Bitcoin's up. Uh, MasterCard or something on top of Elon a couple days ago. It's amazing. I got a ticker on an old iPad. It's 48,165 right now, but I think the maximum I saw was 48.6. I haven't been watching it the whole time though. So I've already done a lecture today and did some grading. So I'm kind of tired. I think you guys know a bit about networks already. So I'm just going to kind of go quickly through these slides and comment on some things. This time I actually kind of previewed what was going on before I started recording, but just briefly, and I kind of have an idea of one of the things I want to point out. So I think it starts right at the beginning. It's kind of getting first of all, what is a network? A network is just some kind of infrastructure that allows computing machines, I want to say, in the context of this class. It could be computers, it could be phones, it could be other types of things with processors in them. It allows them to communicate with each other. My light bulbs now are on a network, so they have a little bit of circuitry that allows wireless signals, and it also interprets them in order to like change colors and turn off and on and stuff. So, but a network allows communication. Why are they choosing now to bark? All right, so I kind of want to jump on on top of some of the common things you'll see. We don't need to see the topology. Okay, topology. Okay. I cheated and went and looked real quick. But I was right. It means place in Greek. Topos means place. So it's the study of places in a way, but you can think of it as study of shapes. Topology in mathematics is the study of like different shapes in math terms that are defined by functions and stuff. So a torus, for example, and what are the characteristics of those, and how a coffee cup and a donut are both tori, I guess, tori. Anyway, in terms of networking, though, it's the shape of the network. So these are the three most common. This is true. There was one that was a lot more common in the past. I don't know if you ever see them anymore. And I'll just add it as a bullet point here. Ring network. And I'll briefly discuss each one of these just to point out what the slide. I don't know if the reading talks much about it, but I'll tell you what the slides don't show. So a star network. So star network is where you have a central thing, whatever it is. It could be a computer, it could be a router, or whatever. And then you have satellite computers, like spokes of a wheel off of that. The thing about a star network with the central hub is that if you take out the hub, you take out the whole thing, right? If you take out any of the individual computers, though, you're okay. There's this thing, a concept that comes up in networks that's not really shown here. It's a graph theory concept called cut size. Yeah, cut size, if I remember correctly. I think that's the term. Cut size is how many cuts you would need to do to divide the network in two. So the cut size of a star network is 1. If you cut any of those blue lines, you've cut it into 2. But in a way, if you hit the hub, you've cut it into 0, right? I mean, there's no network then. They're all separated if you cut the hub. But if you cut one of those spokes, then you've got one computer in a network by itself, which is not a network, I guess. And then you have the rest, right? So one of the things you want to, that's a topic, a planning kind of stage thing for networks is how big the cut size is for like fault tolerance, and if one thing goes down, or can you still route around that damage. Sort of the early idea of the internet was meant to be a way for sites that are not co-located to share information over electronic network, but it's also, if this is actually an urban legend or not, I keep meaning to check on this, but my understanding was it was supposed to survive nuclear attack, right? So it was supposed to be designed in such a way that if you killed like a big chunk of it, it would still be able to function on a wide scale. So that's something you want to think about with networks. It's like, how much damage can you do to a portion of the network and then still have it function at whatever percent capacity, including 100, ideally, right? except for the part that gets knocked out, of course. But the remaining part to fully function. So bus network, you need to have some kind of termination on each end of the bus, but then things just plug into like a central line that everything comes off of, almost like a road or, sorry, hit my arrow key when I was gesturing to some nobody. You can't see me, but anyway. So yeah, they're connected to like a backbone, I guess. This is what the term they use here. A mesh network, this is what I was talking about. This is not a good picture of a mesh network. So you know what? So pause plus Google. So a mesh network, the idea of a cut size that I was giving you before, this is the important thing about a mesh network is that for a 2D mesh like this one, so each of these dots, this is related to graph theory. This is where I'm getting some of this, but how you would compare this to graph theory or show that it's an adaptation of graph theory is that each node on here, each of these vertices, the black circles, represents like a computer or some kind of device on the network. And the idea is this is a wired network too, not wireless. Wireless mesh is a little different. There's probably some kind of correlation on some level. It does have this idea of redundancy and being able to route or find the best path. So the more nodes you have wirelessly on a mesh network, the more stable the network is, and the better it performs. Anyway, so in this particular case, if you have 2D mesh, you just imagine these computers are like laid out logically like this. Obviously, they wouldn't necessarily be in a square that's a certain size, right? But if the connections between them would be symbolized by each of these things, these lines. So these like the wires between them. If you cut the connection between these two computers, they can still talk to each other. I'm trusting that you can still see my mouse here. See how that's one route, right? They could also go, I mean, if they had to, it would have to go all the way down here and back around, right? So that's a 2D mesh. 3D mesh, so you can cut it in one place. It takes two cuts to at least two cuts to separate this network into two pieces. So if you did a cut here, for example, and a cut here, this node would be isolated. Depending on what parts you want to separate from each other, you might need more cuts, but you need at least two. If you just do one cut, they can still all talk to each other somehow or another. It might not be the short distance, but they are still able to get from one to the other. You have to do at least two, usually one of these corner ones, in order to separate the network into two halves, two parts. So the part where you have one node and the part with everything else. For example, if you want to isolate this node, you have to do 3 cuts. See, if you want to do these 3 row columns over here from these 2 columns, then you have to do 1, 2, 3, 4, 5 to actually divide it into 2. Now, that being said, if you make it into 3D, the more edges you add to each node, the more cuts you have to make. So you have to do at least 3 for a 3D mesh. So it's the cut size is the number of dimensions, the number of connections each thing has. So you'll notice that everything in this network has at least 2 edges. That's the cut size. All right, and another specific adaptation of a 3D mesh is something they call it a torus here. This is a better picture of it, I think. I think this is a 2D torus. Yeah, so a 2D torus is like you get to the end and then you wrap around to the far side. So you could do the same thing with this, right? And that's what it would look like in this picture. So if you imagine that this is the same thing, except this node right here will wrap around in a 4th sort of dimension to this one over here and increases the cut size. So that's a little bit more about what's going on here with these network topologies. There's one more, like I said, called the ring topology. Do they have an example on this page? There's a hypercube. You got a bunch of different things here that gets way too complex for what we're covering in this class. So don't worry about all this. This is the more advanced stuff that some of you might do if you go on to a 4-year or even grad school. That's a lot of graph theory and stuff. But a ring, I'll just describe a ring network. Just imagine a ring of wires with nodes all around it. Let me actually just Google. Okay, this would be a ring network. Anything that's like this shape. And the way it usually worked is you would have something called the token. Kind of think of it like a speaking stick. And what would happen is this token would go around the ring. And if something had a message for something else on the ring network, it would load it onto the token. And then that token would travel around and would drop it off at the next place. And it just would continually go around in a ring. So aside from just the shape being in a circle, there was this whole idea of a token as well. They're showing it here, the flow of the message around the ring. Let's see if you add the word token, if they show any more about it. Yeah, this is kind of show. So there's tokens moving around in a circle, and it picks up and drops off as it goes around the circle. Notice there is a cut size of 2. There's still a cut size of 2, because if you cut right here, you can still go, like this. It probably actually breaks the ring network. I'm not an expert on how ring networks were created and how they function, so maybe it actually would make it fail because it has to keep going around in like clockwise or counterclockwise order. But still the cut size to separate this into 2 would be two cuts to isolate one. Just graph theory speaking, not design. Somebody knows more about ring networks, feel free. But it was left out, and I thought I should add it because it's usually included as one of the basic topologies of networks. Let's get back to the slides. So I'm trying not to go on too much detail about these, but you just kind of want to know in general terms what these things mean. LANs originally had LANs and WANs, and this has kind of been added recently, in my opinion. I don't know how far back the origin of these two terms are. I've never seen MAN, as a matter of fact, until this book that we've adopted. PAN is sort of personal area network, is something I've seen fairly recently, but back in my day it was LAN and WAN. So a local area network is basically it's the network you have in your house or your business. It's everything's connected to an infranet, maybe. I'm still not infranet. That's an undernet. An intranet instead of an internet. So like your business might have a connection to the internet somewhere, but you have a bunch of computers inside on a local network. Local area network. It's just a local area network is confined usually by space to a particular limited area. I do want to say the local area network, intranet anyway. An intranet could be spread over a geographical location. So it's isolated from the internet, but it's inside the business, for example. And it could be like across the country even. You would have an intranet. I don't know if I would call that a local area network. But the classic idea of a local area network is the LAN party, like LAN. So back in the day before the internet was a big thing and wireless routers and stuff, I've done this myself. I had a little four-port Ethernet hub. Take it to my friend's house. They had 2 computers. I had mine. I brought my computer, and we had 3 computers. We played Diablo 2 on a LAN network. We hook all the wires up and start IPX, whatever that was back in the day, and then they had TCP IP protocols that you could do over your little LAN. And I use an Ethernet hub, and I want to talk about, because I don't see any slides on this. I don't remember if they're reading either. So they do talk about switches versus hubs. So in Ethernet, the way Ethernet works, and I know this needs to be part of the curriculum in this class too. The way Ethernet works is it's just a big party line. I don't know if you guys know what a party line is, but it used to be telephones would different houses would share one switch. And you would pick up your phone, and if somebody else was already, like your neighbor was talking, you could hear your neighbor. You could eavesdrop on your neighbor. That's a party line. An Ethernet protocol is kind of like that. An Ethernet network is quiet most of the time. It's like the idea of space and matter. Even like your desk is mostly empty space, right? There's more space inside or in between the atoms than there is actual hard matter, and where hard matter actually is gets into physics and stuff. But it's kind of that idea. Most of the time your Ethernet network is quiet, even though you might be seeing traffic all the time, but little pulses of messages are sent really quickly over the electronics, right? And then it's quiet. So most of the time, if you have a bunch of computers hooked up to an Ethernet network, they can all be listening for messages that are directed to them. If it's not directed to them, they just ignore it. They still hear it, but it's like, oh, that's not for me, and it just passes over the network. And when it is for them, they take it, process it, and then they transmit it back. Every now and then, two devices on the network will try to talk at the same time, at the same instant. If that happens, something called collision detection. There's ways you can tell that the message is so garbled up that it's not a valid Ethernet message. That allows the circuitry to be aware that there was a collision, is what it's called. And then each device will be notified that their message was not delivered, there was a collision, and they will both back off and wait a random amount of time before they try again. Because it has to be random, right? Because if they've waited the same amount of time, they would collide again. So they both ran, let's say, okay, roll a dice, I'll go in 2 seconds. Actually, it's on the order of milliseconds, right? But I'll wait a small amount of time, you wait a different small amount of time, and then we retransmit. And more than likely, we won't collide. I do know that when we had 3 or 4 computers on a Diablo 2 network, there was a little light that let you know every time there was a collision, a red light, and it would light up quite a bit at some points in the game when there's a lot of stuff going on. So that's opposed to a switch, which your reading does talk about. A switch has electronic logic built into it to where the message goes to the right port without this whole party line deal. The switches are more reliable and quicker, but more costly and more complex than a hub. And so if you had if you had Ethernet and you had a switch on the Ethernet, you can isolate signals from each other and you don't have as many collisions. I'm not a network person, I'm a programmer, but that's my understanding of how all that works. Your mileage may vary if you know a little bit more about it, but that's the main difference between a switch and a hub. Now then you have the router. A router uses programmatic logic to determine where to send things. It routes traffic from here to there based on the design of the packets and the headers in the packets, and then like a logic about where things should be sent in order to have optimal traffic control over your network. So router is like, it's a more abstract idea than the electronic level of what a switch is. So personal area network would be like your phone and stuff. Anything that's like kind of you wear on your body and carry around. And then I guess this is where you have, like, if you're downtown, maybe they have a little network for Market Square or something. That's what I'm imagining. I don't know if they do, but you could imagine. Or a campus. That's a perfect example. I'm just seeing this right now. But campus, UT has like their network for their students, and they'll like have credentials where they can sign on across campus. I think even Pellissippi has this, right? If you're on campus, there's a little campus network for Pellissippi that you can sign up for your phone to be on. All right, so I mean, these things existed. The MAN, even back when I was a student, we had a MAN, and we didn't call it a MAN. I think we just called it like the local wireless net. I don't even know what we called it, but whatever. So it's just showing. I'm kind of going to go quickly through these and let you guys do because I'm trying to make this a shorter. I feel like you guys grew up with networking, so a lot of the stuff you already know. I'm just going to point out things that I think are significant. So a WAN, a wide area network. Large geographic regions. There are all kinds of different WANs, but the biggest WAN is the internet itself with a capital I. And internet is an internetwork. It's a network of networks. It's a way of bridging two networks that they might not even use the same protocol, but you can connect them together using some kind of common language like TCP/IP, for example, which is the language of the internet with a capital I. And that's the widest area network. So again, a WAN, your intranet for your company might be considered a WAN if it's all around the country, but isolated from the internet, it would still be a WAN. The truth is, those internets are going to be going over internet backbones, and then you're using authorization and authentication to separate that out for credentials inside the internet. So, but anyway, if you have some kind of network, it's over a wide geographical area. It's a wide area network. But again, the widest area network is the internet itself. All right. So client server architecture. I mean, you guys, I think you know what client server is, but yeah, I'm just gonna leave. I mean, obviously, database server. I think the point here is that you're not sending all the data across the network when you do a query. I don't know if that's true. Like, I know the way some database protocols work, you got a database server. That's where the server is in this particular example. There's all kinds of different servers. You got web servers. That's another server. The clients is the web browser you're using to view the web page, right? You got the whole dumb terminal mainframe computer. Like UT used to have things called VAX accounts, and a Cafe was the program you were given. Students would computer access for education is what it was called. You had I think you had a certain amount of time per month that you could be on them or something, if I remember right. But anyway, those were dumb terminals that didn't have any processors in them except for what you would need to run a monitor and a keyboard, but didn't have a CPU in it, right? It would talk to the mainframe computer that was at the bottom of the spam can, if you know what that is on campus. I forget what the name, the Stokely Administration Building, maybe. It's across from the Hubert Hodges Library. But anyway, that's a classic client server kind of thing. But for the database, sometimes you'll like create a query and it gives you back like a whole, I don't want to say a whole table, a data set is what it's called. And you might get a pared down. I'm trying to think, is that true? You get a data set which is in memory. You work on the thing in memory. This is one way to reduce the traffic on a network. You get like the table back and then work on that data set, and then like say you're going to save something back or something, then the thing in memory is transmitted once you've set what it is. Anyway, that didn't make any sense. Don't worry, it didn't make a whole lot of sense to me. I think they're just giving you examples of client server networks and maybe some ways that you can minimize the traffic. Bandwidth, speaking of minimizing the traffic, bandwidth is how much data you can send over the network at a time. So it's usually measured in so many bits per second, whether megabits, gigabits, that sort of thing. Oh, it says it right here, bits per second. Think of bandwidth, it's like this way. This is why I want you to think of it as throughput is a similar term, I think. Throughput is the amount of data you can send at once over a network. So if you have more throughput, you probably have more bandwidth too. And the way this works is, imagine like a little alleyway in a little European city compared to the Autobahn or the interstate in the US, a big highway with like 5 or 6 lanes on each side. Those bigger sections of the network will have more bandwidth, and you can send more data at a time. So that means you can send data faster, because you're sending more at a time. You don't have to squeeze it through a smaller space and send less at a time, which takes longer to send. That's opposed to something like ping time or latency. A lot of people get confused on these two things. So latency is the turnaround time on even the smallest bit of traffic. So if you imagine a little Hot Wheels car going down the biggest interstate superhighway system, how long would it take it to go from one end of that to the other, say from Atlanta to Knoxville on the interstate? That's latency, like the fastest it could go. But if you took like a whole fleet of cars and sent them, it might take longer, because you'd have to manage that traffic. Maybe you'd have to, like if you had 20 cars and only 5 lanes. So these are the concepts you want to be thinking about as far as bandwidth goes, and latency. Ping time is another way of saying latency. So often when you're playing, say, a video game, this is an argument I get into with people. with sometimes. The ping time usually is what matters, the latency, because the traffic you're actually sending for little updates about where your location of your character and where the bullets are and all that kind of stuff is not necessarily that amount of huge traffic. What's more important is how long it would take even like a single little signal to go from one end of the server to the client. That's more important in like game performance, as far as being the thing being where you think it is when you shoot it, that sort of thing. That's the latency compared to downloading a huge movie to watch. You need bandwidth for that. So like a huge movie being shoved through the pipes to you, the bigger the pipe, the sooner you get that movie. Whereas if you were using that same pipe for playing a game, it's like shooting a little pebble through it, right? So that's the way you want to conceptualize these things. Wired transmission, wireless, I think you know the difference about that. You do want to be somewhat, this is basically phone wire, twisted wire, 2-wire, sometimes it's called. This is what you had on the phone network for the longest time, and it's not as fast as like coaxial cable. Coaxial means it's got a common axis, right? There's several different cables. There's like a wire, aluminum mesh around this like plastic insulator, and then inside that there's a copper wire. I don't know the electronic engineering of it, but that's coaxial is usually faster than 2-wire. 2-wire has interference problems, for one thing. I know that the signals interfere with themselves in 2-wire. And then you've got fiber optic, of course, which is the speed of light minus however much it's reduced by going through the substance, like the fiber, the glass, whatever it is. Very expensive. And what I should say about that too is like, we were just talking about a faculty meeting today. We were talking about like doing stuff on campus versus doing stuff remotely learning. One of the things, like if you have a lab where you're learning how to cut fiber optic wire and splice it together, however that's done, it's I remember seeing the little cut, this very exact thing. If you mess it up, it's very expensive to fix. So, but of course, fiber optic's really fast. All right. Anyway, wireless technology. What do you need to know about this? They give you the frequency ranges. One of the things I want to point out, it says microwave. One of the things you want to, my understanding is correct on this. Microwave it's higher energy than visible light. It's shorter wavelengths. And it's basically what you've got in your cellular data and your Wi-Fi, all the wireless stuff that you know is microwave. Which you think about, I'm not a tinfoil hat person. I don't think you're getting brain damage or anything. Some people do. Maybe the jury's still out on all the stuff I've heard about. It says it's not dangerous, but I do want to point out, I just think it's something to point out, is that Wi-Fi is microwave range. Now, it's not the microwave range that's used for microwave ovens. Microwave ovens are specifically, if I remember my science correctly on this, it's water is a polar molecule, and the wavelength of microwaves are like the diameter of that molecule somehow. So as the waves go through because it's polar, it's got like a fat end and a skinny end or whatever, it makes the water molecule oscillate with the waves because those waves are precise. So basically you're heating up the water in something. I may be wrong on this, but so just to saying this in the microwave range, microwave just means small wave, right? Tiny wave. So the microwaves you have for cooking stuff, making water oscillates a microwave, but it's not the same size wavelengths as you have for transmitting stuff over your wireless network in your house or your cellular phone. Infrared, of course, is below visible. It's below red. It means under red, literally, right? So red, the red side of the spectrum. Underneath that's longer wavelengths. It's, I want to say, disadvantages. Must have an abstract. interception. I wanted to say like longer wavelengths though. Radio waves are very long, and they more easily go through solid things. But you know what I'm going to do is I'm going to exit out of Discord. There we go. All right. Near field communication, that's what you use for Google Pay and stuff. I say Google Pay, Apple Pay, whatever. The new wireless, the tap credit cards, that's near field communication. The things you use in Atlanta Metro to open the gate, that's near field communication. London does this too now. It used to be you stick the card in and it had a magnetic stripe and you pull it. I like the way it was cool. You pull it out on the other end and that would make the gate open when you pulled it out. Now I think it's like, I want to say when I was in London last, they have, what is it, the client Oyster card. I think that's near field communication. I guess it's easier to, it's less wasteful because you can reprogram, load destinations onto the same card, right? Instead of wasting a bunch of paper, magnetic paper. Anyway, and Bluetooth, notice it's like a Viking ring for, rune for, like, I guess the B sound. I think it's just a cool symbol for it, but I'm not sure what the wavelengths for it are, but it's a greater distance than near field, but still smaller than like Wi-Fi. I want to say my Jabra earphones that I got not too long ago, they say 70 feet, I think, but you know, it needs to be like out in the open. It can't be in your house. If you go in the other room, it starts breaking up. And if you're walking or running, if you've got the wrong angle on it, I noticed it doesn't work. If you had the phone like out in front of your face, it's fine, but if it's down along your body, if it goes through your body, sometimes you get crackles. But all right, this is just like a table. I don't want to go into the detail about these, but these are just like, it's kind of I want to say it's the evolution. A, B was A for, I want to say, how long ago was A? I feel like A's after. B's what I remember first. Then I remember G and N. And I forget how A and AC work. I've lost track of it. At one time I understood what all these were, but they're different frequencies and different speeds. I would just, you're not going to be tested on memorizing all this. So don't worry about memorizing this table. But I say that I should hold on. Yeah, I checked. I mean, this should be on your study guide anyway, but you're not going to have to know all these details. As though it's a good rule of thumb to have an idea about the frequency ranges and the speeds, especially. That's the practical everyday thing you want to know about them, right? When you're actually working with them yourself in your house, like, which one should I get? I will say you get faster speeds from the shorter wavelengths, but they don't have as much of a reach. So there's the whole 5 gigahertz versus 2.4 gigahertz. 2.4 gigahertz has a longer range. 5 gigahertz is faster transmission speed, but it doesn't have as far as a range. And I don't see where it says that in this. That's important. I think that's probably the most important aspect of it. Those two things. All right, let's see if they stop barking anytime soon. Oh, it's sirens. Here's a sample of what happens every time there's an ambulance or a police car. All right, I think they're done. So I hate hearing barking. It annoys the crap out of me, but I usually think the howling is amusing. It's fun, but not right now when I'm doing this. So anyway, the good thing is you can just say, "Hey, babies, shut up." And anyway, let's get back on it. So what you do need to know is, and I think this is on your study guide, but sort of the range of distances for all these things. So keep in mind what the shortest distance, what you want it to be the shortest, right, is NFC, near field. What's even in the name, near field communication. Just remember that, and that will give you the answer. The nearest field is near field. And of course, with credit cards, you don't want to be like somebody walking down the street with a payment processor and because you're within 10 feet, right? You want it to be almost touching. if not touching. Anyway, near field's the shortest. And they're just showing you what you guys know how this stuff works. I'm not going to go in detail about it unless something jumps out. It's talking about microwave again. Microwave actually is a pretty wide range. 300 megahertz versus 300 gigahertz, million versus billion. That's a big range. So, then it's just showing you kind of the evolution over time up through 5G. 5G is so new. My phone's 4G still, or LTE. I don't know the difference really. I know there's a couple of different types of 4G as you see here, but I don't know. Does anybody have any 5G phone? Let me know how it is, because I know it's supposed to be in. I feel like people have 5G. They have the phones maybe, but maybe the infrastructure's not there yet to really exploit with the phone. I don't understand. This is one of those things I need to get up to date with, and it's a constant job, right? Keeping up. So anyway, so again, let's look at this briefly. So modem means modulator, demodulator. Let's see how it describes analog signals. So what happens is you take your digital signals for the network signals, turn them into phone pulses, analog phone pulses, send those over the telephone network, and on the other end, another modem, modulator, demodulator, will take those analog signals, those pulses, whatever, and in that is encoded the data that can be turned back into digital. So that's the way it used to be done. It's kind of a kludge if you think about it. It's like, hey, let's take this technology we got, let's encode things. One of the things you want to learn about IT and computer programming in general is that things can be encoded so many different ways. And that's being able to encode information signals is the solution to so many problems. So you got this problem here. I need to talk to another network cheaply over existing network infrastructure. What is the network infrastructure we have? Pulses of sound, or it can carry analog sound, right? Electronically. How can we exploit that? Well, we'll create a device that will take digital information, bits, zeros and ones, and convert that into pulses that can be transmitted over that network, and at the other end can be converted back to digital. So that's what a modem was. What else do you need to know from this? I talked about switch as physical device address and each incoming message on the network to determine which output port. The idea here is there's electronics that use a physical routing kind of thing. So you figure out the address in each incoming message and the physical device address, and then you send it to that appropriate hardcore metal port, right? The actual electronics. And then a bridge will connect a couple of different networks together. It's the same both LANs here. I didn't ever think about it as LAN specifically, but yeah, I guess that they would need to use the same protocol. So that makes sense. So you might have a bridge kind of mode for if you had two wireless access points in your house. You could put one of them into like a bridge mode, and that would allow you to extend your network a bit. I've done that before. Better idea is to use the routers that are built to do that job these days, in my opinion. Like the Google Mesh stuff or all the mesh options, which I guess technically they might be bridges too, but they're more sophisticated than just a simple repeater kind of thing. Yeah, and I guess a router is just two or more distinct networks. So yeah, let's just see how they say it. There is a logic to how the routing works, though. There's an algorithm, and there's different kinds of routing. So there's more logic into how the traffic gets routed, gets sent around when you use a router. I think that's the easiest way to describe, in general terms, what a router would be. And then a gateway is, you might have an intranet at your company, and then somewhere on that network is a connection to the internet, and every device on the network needs to know where that is if they're sending traffic to the internet somewhere something out on the internet. You need to know where that gateway is. Okay. Network operating system. I don't think we need to know this necessarily. So I'll let you read about that. I remember the NOS was Network Operations Center for like an ISP or something, but this is just talking about like you would use a network operating system, and it would be like something like NetWare or something like that. That would organize how things work on your network, like how you talk to the printer and that kind of thing. Like Windows Server would be another example. There's something else I'm trying to think of, and it won't come to my mind right away. But yeah. Hold on, let me see if I remember. Okay, so I had to look it up. Samba is something like that's a way of allowing Linux computers to talk to Windows work groups, that sort of thing. This is the idea of a network operating system. So it's not important to really get stuck on this particular concept, though. And yeah, this is not all that important either. I'll let you like read about it. There was something I wanted to get. Oh yeah, I wanted to get to this internet stuff because it's my favorite part. So this graph, when I looked at it, I'm like, it's kind of scary because I first got on the internet. I'm going to say 89, 90 wasn't the first time I ever did anything on the internet. It's because I went to college. I didn't have like a modem on my Commodore 64. So it wasn't until college that I did anything on a network. So there were two main networks at the time. There was the internet itself, and there was something called BitNet, which was more of a local, I want to say it was a WAN in the Southeast, or maybe it wasn't even the Southeast. It was just like, I'm trying to remember how BitNet worked. There was a chat thing on it called BitNet Relay, and it was basically the Pepsi Cola version of IRC, which is Internet Relay Chat. And I remember being on BitNet Relay back in the day, and I remember BitNet email addresses that had something to do with an percent sign in the address instead of an ampers at. Shoot. Anyway, but I was on the internet way before 94. 94 is actually what's significant about 94, maybe not January 94, but definitely in 94, that was the year that the internet was opened up to commerce, because a lot of you might not know this, but before like 94 or so, the internet didn't allow commerce. You couldn't conduct business on the internet. It was all academic and military stuff. So I want to say, I think you could I can't even remember what the rules are. I remember because I was never doing it. It was never a concern of mine. So, but I remember being on Usenet news groups, and I'm wanting to say that they didn't allow like buying and selling stuff, like a flea market swap meet kind of deal. I remember there was a famous spam on the Usenet networks that you would see all the time, where the post would be sent to like all the main groups. It was called, all caps, it was "Make Money Fast." That was the name of the post. I wonder, hold on. Okay, wait, Wikipedia comes through on it. It was a chain letter kind of thing. I remember it had the dots. I remember that was the thing about it. Somebody named Dave Rhodes, I guess. But yeah. Oh, here's the legal part. Perfectly legal. So I don't know. Maybe it was like some kind of pyramid scheme or whatever you call it. But it was a chain letter. I just remember people were annoyed by it, and I would see it occasionally myself out in the wild when I was on Usenet. But anyway, what I want to get, the thing about this slide is like maybe 3 or 4 years before this slide starts is where I was using the internet, and still it's zero right here. And I mean, it doesn't mean there's no computers, right? They're just not measurable because the scale is so huge. You're talking about several thousand. I don't know how many thousand. I could probably go look it up. I don't want to go look it up, actually. At some point I should. It's good information to know, but I'm just struck by the scale of this graph at the fact that it doesn't even register how many computers there were on the internet, how many nodes, domains, whatever, servers, machines on the internet. In 94, in relation to the first tick mark, that's how fast it grew, right? So like, let's say there were 200 million by July of 2003. So here it's like, it's still probably a few tens of thousands, maybe I don't want to say even 100,000, who knows, but just how fast it grew. But yeah, this is when, about this time is when AOL online and stuff came into the picture. There was something called Delphi that was before AOL. You had Prodigy, Delphi, CompuServe. These were like online ways to get your computer's network together and talk to other people over the computer. It wasn't necessarily the internet. AOL was not on the internet originally. AOL was its own WAN, I guess you would call it. It had its own servers, and you would call up, and those servers would talk to other AOL servers, right? It wasn't, if you want, I remember, as a matter of fact, the first time that you were able to send an email, and I wasn't AOL, I looked down my nose on AOL. I think there was a short period of time when they had the free discs, right? You could try it out, where I had an account and messed around with it a little bit, but I was already on the internet before then, so I'm like, I think the only thing I was really interested in was it called Neverwinter Nights or whatever, the game that they had, the MMO. But anyway, I remember when they first opened up AOL to the internet, it cost 50 cents to send an email message. I remember that number, and I remember thinking it was so outrageous that it would cost like several times what an actual piece of paper, snail mail, which, snail mail is the term for non-email, right? Because it takes so long. I don't know if you guys know that term even. We used to call real mail snail mail. Sort of a put down insult. What's the word? But anyway, 50 cents to send an email or receive one from the internet originally on AOL. I remember that. I know maybe it's an invented memory, but look it up. I'm pretty sure. So that's the time we're talking about here. So next slide. There's some interesting slides here. That's why I wanted to talk about that. So internet censorship. So some companies try to control internet content services, sure. Like China, for instance. That's the big one. They control exactly what you can see. I know places like Philippines, some of the ISPs are kind of, I want to remember what the dynamic of it is. Is that are they kind of ruled by Facebook? So you kind of sign up for Facebook basically, and you don't get the rest of the internet. I don't even know what the deal is. That's not necessarily censorship, but it is in a way. But then there's also censorship in the U.S. So despite the fact that the U.S. military, which we all paid tax, and I'm going to preach a little bit here, we all paid taxes to develop this thing, the ARPANET, which you see right there, the Advanced Research Projects Administration Net, later called the Defense Advanced Research Projects Administration Net, so DARPANET, and then they changed it back to ARPANET, back and forth. I don't know what it's called right now, but ARPANET's fine. It's the Department of Defense, 1969. Right, cooperation with some academic institutions like MIT and Harvard, I think, and Berkeley, to create this network of networks. And the whole idea that you could like take a computer that has its own certain network language, right, convert it into TCP/IP, Transmission Control Protocol / Internet Protocol, packets of information. The whole thing about the whole revolution in the internet TCP/IP protocol is the fact that you can break one message, one signal, up into lots of little packets. Each packet would have routing information in it. It would have a payload, which is the actual content, like if it's part of a picture, part of a text document or something. And it would have some other housekeeping stuff, like how long it would take before you would give up trying to send it, a time to live thing. There's lots of you guys can look this up. I won't belabor it too much, but you break it up into packets, kind of disperse it over the internet, and once all the packets get on the other side, you would have a number of packets. You would know how many packets were in the signal, right? They would be put back together in the right order. The idea is that things could, like, the information can flow around rocks, and I'm saying metaphorical rocks, right? Issues in the network, maybe so they're slow down here, so the packets start going the other way, or rerouted until they get to the other side where they're reassembled into the cogent message, the actual information. If anybody does anything, then cul-de-sac. We got to know about it, dogs. Okay, so I was talking about how the packets kind of flow around, and I think of it as like Plinko on The Price is Right. You had a bunch of Plinko, and then they get to the other side, and then they reassemble in the right order. That's kind of like, that's a very simple-minded explanation of what's going on with the internet, as opposed to just like having to send, like having a dedicated line between two things and sending the signal over that line. That's what's eliminated in TCP/IP, but also the common language. So as long as you can encode your message as TCP/IP, a computer that speaks, in quotes, another language, another networking protocol on the other end, as long as it also understands the encoding of TCP/IP, it can convert that message, those signals, that information into its own language. So you can have Macs talking to PCs, basically. That was another revolution of it. They didn't have to be all the same kind of computer. So those two things together is why it kind of took off once they got the, I mean, it took decades to get it really up to the point that it is now, right? But that was the revolution. But what my point about that is that we paid for that. That's our tax money. That's the Defense Department, along with, cooperation from private institutions as well. But we paid for that. We also gave so that companies, originally it was like bulletin board systems and stuff on AOL, discussion boards, right? You didn't want to make it to where somebody could sue AOL or the BBS, the bulletin board system, or whatever, for something somebody else, a third party, said. So defamation, for example, somebody slandered somebody. You couldn't sue the host of that material. I mean, you used to be able to. You could, until the Communications Decency Act was enacted, and one section of that was protections for these systems to where they were immune to being sued as long as they took some kind of good faith effort to moderate the really bad content. So the problem with that is that whole good faith effort, what it's turned into is editing and publishing. And I'm sure somebody's listening to me is disagreeing, and you're wrong. It's the newspapers can be sued if they publish something that defames somebody, as we saw with what's his name, Sandman. They settled with him, but he had a good case, obviously, or they wouldn't have settled. Because publishers edit content, they editorialize, they publish, they make decisions about what should and shouldn't be printed, in quotes, by their newspaper. The idea is that AOL and then later on Twitter and Facebook and all these companies don't do that except to get rid of things like obviously illegal things like threats and certain kinds of exploitation, that sort of thing. So you give them good faith effort that they're going to do that job. You don't prosecute them if a member goes and insults another, not insults, that's not illegal, but if somebody defames, libels somebody else. So in other words, they've been given government protection, but they still choose to censor our speech. It's not right. Something's got to be done about it. So this is within the purview of this class. I'm not going to test you on this. You don't have to I'm a big believer in freedom of speech, and you're not going to be obligated to agree with me on this. I might, I'm not going to ask this on the exam. I could fairly say, what does Mr. Nicholson think about this? And then you would have to answer correctly, right? But it doesn't mean you have to agree. But I'm going to tell you you're wrong. Like, they have an obligation to. It's not the First Amendment in this case. On top of that, you've got senators and stuff saying you need to do something about hate speech, which is, by the way, protected speech in the United States of America. It's not illegal. That's the government giving directions to a company who then carries out those directions. Say, we're going to start censoring hate speech, and these particular senators asked us to do it. That sounds like an arm of an agent of the government, indirectly, at least to me. I think the First Amendment might come into play. It's something for lawyers to figure out. I'm just telling you, it's not right. what's going on, giving that we, the people, built this thing with our resources. And then we gave them protections. We, the people, gave them protections. If you don't know anything about what I'm talking about, you're interested, look up, just Google Section 230. And there's going to be a lot of discussion back and forth and opinions. But I'm on the side of the people that say that the fact that that exists means that they have an obligation not to censor us. But anyway, continuing on. Internet backbone, of course. So this is part of what's one of the benefits of the commerce getting involved was that, you'd have more investment from companies that have more capital to create huge backbones that made everything faster. The internet in the early days was really slow. And so we talked about TCP/IP. TCP part, that's the part where it governs how the packets are constructed and how the different ranges of bits have to do with the addresses and the payload and the time to live and the other, like the number that it is in the series and all that. That's the TCP part. And then the IP part, it's about how you address things, the dotted quad thing on the internet. And it's more complex than what I just said, but that's loosely speaking what it is. So we don't need to see all this. You need to know what a URL is, though. Uniform Resource Locator. It says web address. I want to say a URL is more than just a web address. It's originally meant to be a one standard way for things. I don't want to say just on the internet, just like any network kind of thing, but primarily the idea is the internet. A standard way of addressing things so that you can know how to get to the resource that you want. Say a web page in this case is a URL. But there are also URLs in the old days. I'll give an example. So this is just kind of a random example. I don't know why I can't click on it. But FTP, File Transfer Protocol. This is just the way of saying there's this file on the internet. I want this file. FTP, the URL, you could use the URL to designate that file's location to use File Transfer Protocol, not HTTP, which is Hypertext Transfer Protocol, not the web, but FTP to get it. There's also URLs for Telnet, and also for on your computer. So if you go to a web browser, most web browsers will do this. Let's see if mine will do it. Yeah, there's a URL for, say, your directory on your computer. Let me see if I'm exposing anything that needs not be, private stuff. No, this is good. So if you go and type file, it's not showing it now, but file, : / and then / I guess, because it's not totally uniform is the thing that I don't like about so-called URLs. And then you put something on your local computer, like I did C:. And what you'll notice is it brings up, let's see what we got here. Anything I need to censor? No. So it shows the directories on my C drive, and like you can just go into, you can browse your computer using a uniform resource locator. And what you want to notice about this is Windows. How do you separate file folders in Windows? It's a \, right? How do you do it with a URL? It's always a /. So you see this URL has / instead of \. Up here, right? This is where the URL, this is not a URL, this is telling me what I'm looking at, but this is a URL, and you notice it's : well, it's C:, just because it's the C drive, but / / So that's part of being a URL. So that's why it's called uniform. It's a uniform way to locate a resource, regardless of whether it's a web page or a file or your directory or Telnet location. I want to say MUDs even had URLs at the time, but I might be wrong about that. But because MUDs were basically Telnet, so never mind. SSH maybe. I don't know what all the list of URLs are, but it was meant to be more than just web pages. This is the whole point of what I just told you is this not just web pages, even though that's usually the way people think about it and what they mean when they say it. We won't get into ICANNs, just like responsible for all the domains names are. Domain names are the things you actually type in for a URL to get to the resource. Typically it's the web, like google.com. That's a domain, right? It's a hierarchical tree model, and I saw this slide and I didn't like it because I don't know if they did this on purpose, but they left out mill. So One of the top level domains are the ones at the far right end of the domain before you start getting to the actual folders sort of inside that server, right? So google.com, com's a top level domain. There are thousands and thousands and probably millions of com domains. That's for commercial. Originally, it meant to be commercial. It says all types of entities, including nonprofit, schools, and private individuals, but originally it meant commercial. That's what it stands for, is commercial. So it meant that it was originally supposed to be business. Biz came later, actually. Edu, U.S. universities. You'll notice that universities in other countries, like Oxford, for example, which is in the UK. Let's see what the URL is for it. I actually don't know off the top of my head. Let's put Oxford there. This might vary a little bit. It used to be more standard, and now it's kind of mixed up now. But okay, here it is. It's Ox, which is, I didn't know that was their domain name. Ox.ac.uk. So the top level domain is the country code. So there's for like every country on the internet in the world, I think it's always 2 letters. It's the same as the country identifier symbols, if I'm not mistaken, on all cars. The little oval that some people in America, we don't have it. We don't worry about it. So we put like random stuff like Hilton Head Island and stuff. But it's meant to be identify what country your car is from. 2-letter abbreviation. So, well, I would say that, but it's GB for Britain, not UK. So I'm kind of full of it here. But the AC is academic, right, instead of edu. So edu is an America, because again, America invented the internet. I'm sure there was cooperation from other foreign agents and stuff, foreign people, but it's our thing. And that's why the top level domain for mil is military, because who created the internet? Mainly the military. Again, I don't know who. Well, let's see what Army is. Now, Army does have a .com domain. They talk about this actually somewhere, but you probably don't have access to the mil stuff. Let's see. Let's pause. All right, I had to type www.army.mil, but there's a whole mil. And you guys, here's the thing. I know there's some of you probably who were in the military, so you're probably very familiar with this .mil, and there's probably all kinds of things on the military branches, the various ones. There's stuff on the internet behind the top level mil domain, so you know what I'm talking about. But .mil is specifically United States, plus apparently, is it NORAD, or there's some Canadian thing that is also underneath that top level domain, because we work together on it in North America. But it's .mil because America, right? And then you also have the top level domain for our country, and then for each state. So something.tn.us, you've probably seen this. Here's one. And .gov, that's for government. But the .gov, again, Gov, U.S. government, not anybody else. Why? Because we invented the internet. Not Al Gore. Al Gore, I'm not the biggest fan of Al Gore, at least not anymore. But I think he got unfairly maligned for that and mocked, because he's not saying that he's Bill Gates or something. I mean, Bill Gates didn't invent the internet either, but he's not saying he's a computer genius. He's saying that he was in Congress when they voted for funding for ARPANET and all that kind of stuff. So that's what he was saying, that he was partly responsible for the internet because he helped promote funding of it. So it's kind of ridiculous. People give him a hard time on that. There's plenty of other stuff you can give him a hard time on, but that's kind of silly. What else was I going to say about it? I'm kind of just riffing now. But, orgs were originally nonprofits in Knoxville area. There was early days of the internet before the need for it became obsolete. Knoxville area, like organizations, nonprofits, and also some like government stuff was on something called CoreNet, which was the Knoxville. What did it stand for? It's KORRNET.org, CoreNet.org, Knoxville something network, regional network. I don't know. Anyway, I should look it up maybe, but Org is for like that kind of stuff. And .NET networking sites, I can't even tell you. What was a .NET thing that I used? There was something .NET. Off the top of my head, I can't remember. But of course, like your universities, like www.utk.edu. So these are top level domains, and there's a lot more now. They just added a whole bunch in the past decade or the last 5 years. I can't even remember, but there's so many more that were added. But the whole idea of it is that at the very top you have null. And what I mean by that is like dot nothing. Technically, the full name of this is dot whatever, www.utk.edu dot null. Null is the root. And then from there, you have that top level of several, like they've got how many here? 6, and there were more than that originally, but not a whole lot more. There's mill, and like the country codes were soon after. And anyway, then underneath each of those, you have your domain names like MIT and UTK and AOL and Google and that kind of thing. And then the things in front of that tell you they're meant to give you an idea of which server on that domain you want to go to. So the web server or web servers for Google would be www, right? Now you can usually just type google.com and it knows you want to do a search. But anyway, you get the idea. If you want to do a document online, a Google Doc, you type doc.google.com. In reality, like in the very early days, you were going to one computer. That doc meant that you want to go to the computer that, well, if you type www, you wanted to go to that one computer that was the web server. But then, like you had a whole a network of web servers, and they would handle, randomize not randomize, but route which traffic goes where, that was actually serving up the pages. But all right, it's over an hour, so I think that's about actually it. This slide's very important. This is something I don't know if I talked about it in earlier slides, maybe not, but the internet and the World Wide Web are not the same thing. So when I was first on the internet, there was no World Wide Web that I knew of at the time anyway. It was being developed by Tim Berners-Lee at the Centre Européen pour la Recherche Nucléaire. It's off the top of my head. I'm trying to remember. It's at the European Center for Nuclear Research in, I want to say Lausanne, Switzerland. I spent a year abroad in Switzerland, in Fribourg, which is about an hour and 15 minutes northeast of Lausanne, I think. Lausanne's right on the Lake Geneva, on the other side of the lake, kind of from Geneva. Anyway, he worked there, and he wanted to facilitate sharing documents on their WAN or LAN, their intranet, right? And there were already all kinds of different versions of markup languages, including like teletype type stuff. He created a hypertext in the protocol to deliver it. That's what became the web. So Sir Tim Berners-Lee, who was a British national, but he was working there at the Centre Européen pour la Recherche Nucléaire. My French accent right now is so horrible. Recherche. Anyway, that is the web. The web typically rides on top. I guess you could probably have some kind of web server that's not on the internet, but I'm trying to think. It would still use TCP/IP, I guess, but maybe not. The whole point is that there's a layer on top of that for hypertext, how to transmit those documents back and forth. The whole get and put and all that kind of stuff. Those commands for retrieving web documents, and that's the web. The web, capital WEB. A lot of people do lowercase now, but really it's a proper name, to be honest. It's either World Wide Web, 3 words, all capitalized, or web for short. Still a proper name, should be capitalized. Web page technically should be 2 words, but people don't. That's going to change officially eventually if it hasn't already. All right, that's not the same thing as the internet. Again, the internet existed way before the World Wide Web did. A lot of people think of them as synonymous. It's on the internet. I saw it on the internet, which is true. You did see it on the internet because the internet the web document was delivered to you over the internet to your web client that you use to go attach to talk to over the internet to a web server. But you're talking about a level of abstraction up from the internet. The internet's just the road you're traveling on. It's not the web itself. So make sure you, even if you use them sloppily in everyday life, make sure that you, as people that are studying IT, know the difference. There is a difference between the two. So I think that's enough harping on that. So hyperlink and hypertext. Hypertext, the idea about hypertext originally, people don't usually think about it this way anymore, but for millennia really? When was, I guess millennia if you include papyrus and the Bible and the Septuagint. If you go way back to written records, text was 2D. You start at the top, or it depends on, the Hebrew, you would go from right to left, right? And usually top to bottom. Sometimes they mixed it up in different, like the Greeks would go as the ox plows is what they call it. You would write to the end of the line, and then you would go down a line and write the other way. So kind of like back and forth, like you're plowing a field. Chinese would do top to bottom sometimes, and also I guess probably right to left as well, or left to right. Maybe right to left, I don't know. But it was 2D is the point. You would start somewhere, you would read in a line. Oh, that's the line, it's 1D, but down a page, right? Several lines. So you've got a 2D area you're in. The idea about hypertext is that you could take one of those words maybe and imagine a dimension, a third dimension. You're going up. Hyper literally means above, right? Hyper in Greek. It's the same as super in Latin. They both mean the same thing, above. You're going into a third dimension. So the idea is that you can maybe pick a word or phrase or something in a document. And that document, it's not just what you see in front of you, but it's also all the documents that you can go to from it. And they're all kind of put together in one big hypertext document. So like in a way, some web pages were one big document that was in 3 dimensions. You could like move around within it in 3 dimensions instead of just reading one page. That was the original idea. That's why it's called hypertext. But we don't really think of it that way anymore. You just think of it as going from page to page or whatever. All right, I'm on to, oh wait, I do want to talk about this. So I don't like what it says here, hypertext markup. This is all fine. I don't like this where it says HTML tags tell the web browser how to format text and elements to be inserted. Actually, that's actually correct. Never mind, I do like it. So one thing to understand about hypertext is HTML and the tags and the elements are supposed to describe the structure of the page, not how it looks. Even originally, they originally had tags, and tags are how you indicate elements in hypertext in an HTML document. And again, it stands for hypertext markup language. The markup are the tags. You're marking up the document with these things called tags that indicate the structure of the document. So H1, for example, should be the top level header. H2 should be the one layer down. So if you think about the title of the book, and then H2 should be the chapter, and then a section within the chapter should be H3, and so on. It should tell you the structure of the document, the layout. Not the layout visually, but the layout and structure. So paragraphs and bullet points and that kind of thing. And it could be, then that eventually they did create CSS to separate, because it was all kind of mixed together. Then you could say this is red and this is red, and this is this font instead of this font, Arial instead of New York Times or whatever. Eventually, the World Wide Web Consortium, which is the body that rules how the World Wide Web works now, decided to separate the concerns of try to do it cleanly. It's still not completely clean, but take the HTML, make sure the actual structure of the document is what this is. What's the word? Not adhered to. The purpose of HTML is for that. And CSS is the way your document looks. So you can take one HTML document. The ideal is you could mark up your document the way you want. This should be the top level heading, and this should be the title, and this should be this paragraph, and then the next paragraph, and this paragraph. And you could take that one layout, that one structure, and make it look lots of different ways using cascading style sheets. So cascading style sheets are about how things should look and where things are actually physically laid out on a page. You could take this paragraph and put it over here and this one over here if you wanted. And then if you use a different cascading style sheet, it would filter it a different way. The idea is that the structure remains the same in HTML and the CSS determines what it looks like. XML, by the way, it looks a lot like HTML. As a matter of fact, can be said to be a subset of XML. XML, oh, hold on, I had this planned. It's from W3 Schools. XML, the point of it is that both machines and humans can use it. So a human being can look at this and understand it. If you know a little bit about XML, you can read it. You don't have to be a machine to understand the if it were like an ASCII encoding of binary, you'd have to be a robot to understand it, right? A human being can read this and understand it, but also a machine can, because it's got a consistent structure, just like HTML does. Just the same way that a web client can display an HTML page because there's a consistent structure to that document with the markup. But you can also go look at the HTML and read it as a human being. Same with XML, but XML is more generic, so it doesn't have to be you can use XML for web pages. You can apply CSS to XML and have it look like a web page. You could also take something called XSLT, XML, transform is in there, style, something transform. Anyway, you can take this engine, this computer logic, and send your XML through it, and it will convert it into a web page with HTML tags instead of XML tags. For example, you can make it to where each one of these things is a row in a table, and you would use TD and TR and table and all that stuff. You can have it convert, because the whole thing about, but also you can convert this to a spreadsheet that you send to someone. A printer could print this out if you style it that way or send it that way. You can store logging information. So if any of you guys that ever use Runkeeper, or the one I use with Sports Track Live, when you run, hold on. So there's one for GPS. And the thing is that you can create what's called a schema. It's the rules about how these documents are laid out. And you can do it for, the whole thing about XML is it's generic. You can do it for anything. You just write out the rules, and you can create documents that do things. So in this case, GPX is a way of storing GPS coordinates, or tracks moving around in space using GPS. So here's and the thing about XML is always looks like this. A root element, if you look at this example, breakfast menu is the root element. Notice it's the single root element, and then everything else is inside that. So that's one of the rules about how XML works. So for GPS exchange format, in this example, I can't collapse it, but it's GPX is the root element. For HTML is the root element. You guys have done web pages. It starts with HTML, the whole web page is after that, and then the last thing you do is you close the HTML. So this works the same way. They're both part of something called standardized general markup language, SGML. They're both a subset of that. And I won't get too much into it, but you've got the element name. This is the tag. The tag will have the element name in it. In this case, the root element is GPX. And it'll have attributes that equal something in quotes. That's the typical thing. But then you have these child nodes. So there's some metadata about this whole document. So it looks like it's got the time and a link to who was produced. Garmin, the trying to remember what it's called. Dang it. The GPS unit in your car, right? They do GPS stuff, Garmin does. And then you have something called a track, and this can be very long. And what this will do is it will log positions on the map according to GPS signals. So I've only ever seen one that has one track, but then in one track segment. I suppose you could have different legs of a journey or something as different segments. I've never seen that. But if you do something like Runkeeper, you can convert your route that you run around your neighborhood into this document. And the whole point is you can take this, and as long as the other thing understands how GPX works and XML in general, but specifically GPX, it can take this data and present it in its own way. Take that data and crunch it and do something with it. So like when you're doing Runkeeper, it can plot your map, the route that you ran, right? And it could give you some stats because, you know, it'll keep track of the time and where you're at. See, here's the time. So what you'll notice is that for each track segment, and again, there's just one. You could divide up one track into several segments, but you usually don't. But then you have track points, a series of track points, one after the other. So these can be sampled by your machine, the sensors or whatever, like once every second maybe, and it will it'll add on to this XML document as it goes, and it will say there's a track point, the latitude was this, the longitude was this, the elevation, which is kind of hard to determine for them, but they try, was this, and then I took this track point at this time. And then here's another track point. Notice the times. What is it? 1837. This is also 1837, 31. So 26, 31. Maybe a few seconds, 5 seconds, looks like. In between these samples. Well, this is only 3, but you get the idea. So you would have a series. This is only 3 points. You would have hundreds of points in a run, and that would show your route. So XML is used to generically save data in a structured way so that it can be used by many different things. But also humans could read. You just saw, I read this and could understand it. So that's the purpose of XML. So that's XML and cascading. I won't show those, but they're a way to make things different colors and layout this thing and padding and all that kind of stuff. JavaScript and Java, I just want another note. Remember when we talked about internet versus World Wide Web? 2 different things, right? Same thing here. The only thing, well, it's not the only thing they have in common, but officially the only thing they have in common is the word Java in their names. So they're 2 different bodies. People were responsible for them. JavaScript is logic built into your browser. It originally was just script. A script is like programming logic, commands and stuff that have a specific purpose. So originally JavaScript was meant to do dynamic stuff for web pages, and it was all controlled by an engine that runs in your browser on the client side. So you would have JavaScript code put in, the browser would read it and do stuff based on what the JavaScript is. It was originally called LiveScript, but when Java came out, Java was originally created so that you could write a program once and run it anywhere by virtue of using something called a virtual machine and bytecode, and I won't get into the specifics, but it's a programming language. It's supposed to run on virtual machines. The programs that you create with the programming language run on virtual machines. A virtual machine is a software machine that pretends like it's kind of a computer on top of a real computer. So the idea is if you write a program once, convert it into the machine language, which is called bytecode, for those virtual machines. As long as those virtual machines understand how to talk to the computer, the hardware, you can send that bytecode to any kind of machine that's running that virtual machine, and it will do stuff. So it was originally meant to be used on small devices. As a matter of fact, if you open up, say, a Blu-ray player, and it has that menu and stuff, often that stuff was written in Java with the virtual machine inside. It's meant to be used on small devices. It came true eventually because Java is used to write programs that run on Android, which is a special purpose version of Linux that runs on smartphones. So that's where Java mostly is these days, I would say. It's in lots of other little devices, but in the mid 90s, when the web was becoming really popular, it was very static. You would write a page, you could click around and go hypertext, right? Go back and forth to other documents, but you couldn't get like a dynamic experience where things change on the page. Java was one way to do that. So what you do is you create a virtual machine on like Windows, and then you have a plug-in to that machine in your browser, the Java plug-in, and then you would write Java code, bytecode, that you could send to that plug-in and to the machine, and it would make stuff happen dynamically on your computer. The reason why it was a security problem is because that plug-in that you had permission to do stuff to your computer. So it wasn't Java itself that was the security problem. It was the fact that the plug-in in the browser had access to your machine. It was the problem. There's nothing wrong with Java. Java is no different from C++ or anything else when it comes to security. When you're talking about the language itself, it was that plug-in mechanic that was the problem. But that became really popular, and at the same time, this JavaScript thing, which kind of had a similar purpose, but it worked differently mechanically. Java was becoming popular, so they changed the name to JavaScript. So I guess kind of to piggyback on the popularity. Now, where they're similar is if you look at the actual syntax of JavaScript, it looks a lot like C, and so does Java. They both look like C. So they're also similar, like appearance-wise. But the underlying mechanics are totally different. It was two different entities. It was who were not, I guess they probably talked to each other, obviously, but they were not the same people who developed it. So it's not like Java is like related. It's not like Coke and Diet Coke. It's not something like that. It's like Coke and Johnny Walker or something. I don't know. It's two different companies. So so a lot of times when people mean JavaScript, they say Java. Because Java being used, and applets is what they were called. The things that run in the applet was the code that you run that would run in the plugin on top of the virtual machine. That's kind of gone by especially because of that security concern. That's kind of gone. That's the dodo for that. So Java doesn't really exist in that kind. Java is actually used as a full-purpose programming language, just like C or C++ these days, or Python or whatever. It's object-oriented, blah, blah, blah. But JavaScript's still around. So a lot of times when people say, oh, you need to learn Java so you can do web pages or whatever, they mean JavaScript. So there are different things. We're not going to talk about programming right now, so we might come back to that. I could go on all day, and I don't want to because it's almost an hour and a half. We talked about XML. Web services are sort of like servers that exist to take function input and return a result. So an example would be something that would give you a stock price. What's the current? You would send the stock symbol and it would give you the current price. It's kind of like it's a networked, available, exposed way of creating functions that do things for you that you can put inside of other things. We won't get too much detail about that, but that's what a web service is. Actually, Amazon Web Services are like more sophisticated than that. So I'm kind of, web services might be like virtual machines that Amazon spins up to a service like databases or, cloud stuff, or serve as a back end for Parler, for example, until they pulled the plug on them. So it's a way of buying cloud time to use. I don't know, it's in the technology, so you don't have to actually buy the physical computers, but that's not quite what I meant the original description of web services. Azure's similar in the Microsoft world to Amazon Web Services, so there's a little bit of blurriness where the concepts overlap there. I will say the way you would talk to a web service, and not the Amazon kind, but the one I was talking about with that stock ticker, you would wrap it up it's called an envelope in XML, that language I was just showing you. You would put your parameters in there, and it would return something that was in a similar XML package. So that's a way of standardizing how web services would communicate back and forth with you. I think that's enough for now. I'm not gonna. You guys know about this stuff more than I do, probably. Blogging, that's old stuff, right? Already, you probably know how to do all your shopping and entertainment online. You know this stuff. So, Internet of Things. I think we might have a project on this later, so I'll let you know about that. But Internet of Things is like things that are not just traditional computers that are hooked up to the internet. So cameras and my lights. Hey Google, turn the light off. So Google Home is hooked up to my lights in my house. So.
First you'll have to unlock your
Yeah, I know. That's my phone that heard me, and my Google Home didn't because it's way over there. Hey Google, turn the lamp off. Anyway, there you go. You didn't hear it. And you can have sensors like temperature sensors and that kind of thing. So you know what the temperature is outside over, and you can look baby, monitor your baby. Or we have a light that comes on out here with a camera. We can see if somebody, motion detector. That's Internet of Things type stuff. And those are simple examples. There's a lot more than that, right? You got Nest, this kind of Internet of Things kind of thing. There's a lot of fun stuff you can do with Internet of Things if you get like a network connection on what's it called? Not a Raspberry Pi. You can do it with a Raspberry Pi too, but I'm thinking of the other with the breadboard. It came back to me before I did the search. Arduino, and let me go ahead and do the search because then I can show you a picture of it for you guys who don't know what I'm talking about. So Arduino is like a simple circuit board that has computing processing power, and it can take input into these I/O. You just stick little wires in, right? And you can hook it up with breadboard, and so it's got input and output and power and stuff, and it's got a simple logic, and you can like stick in a wireless adapter, so it's in stuff over. You can get on the network wirelessly, so you could set it up to. One of the fun things people usually do when they first learn it is put a bunch of LEDs in here and do different patterns to LEDs, like a binary clock or something, or have it to where the colors randomly change, that kind of thing. Arduino's really cheap and really fun. I recommend getting one and playing with it sometime. It gives you a little bit more insight into how electronics work at a more basic level than the very sophisticated computers that we carry around in our pockets, right? So I'll let you guys look at the rest of this, but that was the important stuff that I want to talk. It's an hour and a half already, and I don't want to belabor